So, in this lecture we will basically define what inner products are and delve into the inner product spaces. So, we will start with a definition. Let S be a vector space defined over a scalar field given by this R. An inner product function is basically a function from the Cartesian product of the vector space to R with the following properties. So, IP1 stands for inner product property 1. The inner product of x with y, assume that x and y are vectors and each of the coordinates are basically real entries. So, inner product of x y is inner product with y x. Of course, these definitions will change if I define the inner product function as a Cartesian product of the vector space to perhaps a complex number. So, that would basically be a different definition, but here we will stick to reals. So, therefore, this property holds. The inner product of x y is the same as that with y x. So, we have the second property. Suppose I scale the input one of the vectors by alpha. Let us say we want the inner product of alpha x with y. This is basically alpha times the inner product with x and y, and of course we say that alpha is basically a real number here, belonging to the real number. We have the third property, which is basically distributive property. We take the sum of two vectors and we take the inner product with another vector. So, the inner product of alpha plus y with z is basically the inner product of alpha with z and the inner product of y with z. And we have the last property, the inner product of a vector with itself is greater than 0 for all x which is not the null vector, and it is 0 if and only if the vector itself is a null vector. Right. These are several properties for an inner product function. Now, this inner product is a very important tool for signal representation, because we would like to figure out how much of distance we have to go along a certain basis, right, along a certain basis function, how much of distance should we go, and that basically sets up for the coordinates in the signal space. So, it is a very important parameter. So, once we have the inner product defined, we have something known as the induced norm, right. So, in L2 spaces, if you recall, we did L1, L2 so on L infinity, right. We define basically the geometry of these LP spaces, right. So, in L2 for a vector x belonging to Rn, it is an n dimensional vector. If we look at the inner product of x with itself, take the square root of this quantity, this basically is the norm of x. It's trivial to figure out, and this is basically x1 square plus x2 square plus so on till xn square. And if you think about x as basically x1 x2 dot 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 x, that means you have n coordinates. Now similarly for functions we can define this this induced norm, that is we look at the inner product of the function with itself, right, and that quantity is basically xt in the L2 sense, and this is basically integral a to b mod xt square dt, the square root of this quantity, right. So, this is basically the induced norm. So, this is basically giving you a metric of the inner product of a vector with itself or a function with itself. Now once we are comfortable with the induced norm, we can this idea of having one vector. Now we can think about the difference vector, and we can think about the norms over these difference vectors.